Yellowstone National Park sits right on top of a giant, active volcano. This requires attention. Yellowstone has been a national park since 1872, but it wasn't until the 1960s that scientists realized the scale of the volcano. It's 44 miles wide, and it wasn't until the 1980s that they understood it was fully alive and still in danger of a violent eruption. Yellowstone is capable of erupting thousands of times more violently than the eruption of Mount St. Helens 1980. The northern Rocky Mountains will be buried in a few feet of ash. Ash rain will fall on almost everyone in the United States. It's going to be a bad day. Therefore, geologists are eager to understand what is really going on beneath all the hot springs and geysers fueled by volcanoes. Obviously, they wanted to know if and when Yellowstone would explode again, and with what degree of explosion. A major eruption would be an event of low probability, high consequence, as the Black Swan goes, something that could have social and planetary effects. The problem for scientists is that eruptions of these massive supervolcanoes are rare, and the most important actions are invisible, miles beneath the surface, involving chaotic forces, complex chemistry, and enigmatic geological features. One new study has offered insight into Yellowstone's hidden architecture. It models the way magma rises from deep in the Earth's interior and creates two large chambers of partially melted rock beneath the surface of the national park. These two magma chambers were stacked and separated by a layer, called a threshold, like a windowsill, of unmelted rock. Magma rising from the Earth's mantle flows easily and doesn't store much gas. It cools and solidifies as it collides with the relatively cold crust, forming a threshold, which peaks about 6 miles below the surface. The new study, published in Geophysical Research Letters, explains how this geochemically diverse two-level architecture may have emerged over time. One day we may have a snapshot model that says this is the system that looks when there is enough melt for a major eruption. Lead author Dylan Colon, a doctoral candidate in earth sciences at the University of Oregon, told The Washington Post. The study won praise from Michael Poland, scientist in charge of the Yellowstone Volcano Observatory of the U.S. Geological Survey. What's interesting about their model is that they can go back in time and see how that can affect eruption rates over millions of years ago. This new study supports previous research on dual magma chambers. It uses sensors arrayed around Yellowstone to record the speed of seismic waves from small earthquakes passing through subsurface rock. Waves travel more slowly through hot and/or partially melted rock formations. The data gave scientists the equivalent of an MRI showing two magma chambers.